Sagar, just to let you know, I will be there for the first part of the session. In case something else comes up, I might have to leave. Okay? So I'll just ask you to at least stay on for this session, at least for Ajit.
Okay, sir.
Okay, thank you, Sagar. So Ajit, you can feel free to start whenever you want. The participants are being let in, and they have already entered, so you can start whenever you feel.
So let me give them just a couple of minutes more.
Sure.
Can you see my screen?
Yes, sir.
Yeah, okay, great, thanks. The weather is very fluctuating. So suddenly there will be a big wind coming up.
Looks like the remnant of the system that.
Yeah, that is right. It becomes very, very dark. Okay, shall I begin?
Yes, please, go ahead.
All right. So good afternoon, everybody. And I understand there's a fairly large number of you listening to my talk. So I'm going to be talking to you about black holes across their mass spectrum. What do you mean by that? There are black holes, as everyone knows, and these can have different mass. So you can have a black hole of 9 solar masses or 20 solar masses or 10 to the 9 solar masses. Or maybe these are all detected black holes, or maybe you could have a black hole which is 10 to the minus 18 times the mass of the sun, for example. And so I'm going to consider black holes across this whole spectrum. Now, what I'm going to be doing is first to give you an introduction to black holes, then consider the theory of black holes, then I'll talk about stellar mass black holes, and then supermassive black holes, then intermediate mass black holes, and then finally mini black holes. So I've got a topsy-turvy order in terms of mass here, but that's because it's the amount of information that I have on them. Now, this whole project has all kinds of problems associated with it. In order to understand the theory of black holes, you'll need to know general theory of relativity. Some of you may know it. All of you will be exposed to a little bit of it over this set of lectures. And those who don't know it may study it in the future. But right now, what I will do is that I will take some things for granted. I'll put some expressions which are relativistic expressions, general relativistic expressions, explain them to you. Because without those expressions, my lecture will have to be entirely quantitative. So I'm going to be invoking things which you may not be very familiar with, but I'll hope to explain them to you so that you'll have something to take back home. Meaning that in the future, when you read about these topics, so you may understand things just a little bit better because of these lectures than otherwise. Right? So these are not the kind of things that you can find in any one book. There are several. I'll try to list them for you. But as far as the general relativistic notation and the arguments go, I'm using a book which is by James Hartle. It's here with me. It's called Gravity, and it's a marvelous book, really. Hartle is a very well-known senior general relativist, and he wrote this book where, like my lectures today, he actually covered 2/3 of the book and with all kinds of intricacies about black holes without introducing general relativity formally. And then in the last one third or one fourth of the book, he introduces general relativity and then justifies everything that was done before. Right? So I like that approach very much, particularly for the kind of mixed audience which is there in summer schools and the like. All right, so I will not go very fast. I'll go slow. I'll try to explain things to you. Now, for these kind of lectures, where there's a lot of unfamiliar stuff, it would make great sense for us to be face to face, because I could watch your reactions and see what you're finding easy and what you're finding difficult. And then you could ask me questions. And even more importantly, I could ask you questions to see whether you're understanding what I'm saying or you're anticipating what I'm saying. Unfortunately, that will not be possible now. God knows when it will be possible in the future. We just have to live with it. What Professor Dipanjan told me a little while ago is that I could have questions about halfway through my lecture, wherever I like. So let's do that, because always good to take a pause sometimes, especially when there's so much informal material, so much unfamiliar material. So about halfway through, I will take a pause and ask for questions, and let's hope it works. You're free to send your questions using Google Forms, as you would have been told. And if there are enough questions and if a small number of people are interested, then I could even have an informal session with you. I can arrange a Zoom session where some of you could log in away from your normal lecturing hours, where we could have a discussion. So everything is possible. All right. So introduction to black holes. And so let's first see what is the mass spectrum of the black holes. So you've got primordial black holes. Okay, with mass, the only limit is the mass is greater than 10 to the minus 5 grams. Right, so this probably comes from some quantum considerations. And these kind of black holes, we will not be able to form astrophysically. So they must be formed in cosmologically, okay, meaning that in fluctuations in early stages of the universe. It is not clear to me that I'll have time to get into these black holes, because they are associated with the Hawking process. So as you may know, I have 3 lectures on black holes, plus I got 2 lectures on white dwarfs, which will come later in this course. So I thought that if I cannot finish everything, then maybe I could use 10 minutes of my other 2 lectures, 15 minutes of my other 2 lectures to talk about primordial black holes. And so then, the more massive ones, the size of the circles are not indicative of the mass. So these are what are called stellar mass black holes. They typically have mass in the range of a few times the solar mass to about 100 times the solar mass. People thought that they would have masses like 10 solar masses, 20 solar masses max. But after the discovery of inspiraling binary black holes by LIGO, they find much larger black hole masses. And these must be stellar in origin. What do you mean by stellar in origin? Meaning that they were formed with the evolution of stars. So I'll come to this matter later, after establishing the theory of black holes. So then you've got the intermediate mass black holes, say about 100 solar masses to about 10 to the 5 solar masses. So these are generally found in the less extreme active galactic nuclei, some kind of Seyfert galaxies and so forth. And so we'll come to them later. Then another very important branch of black holes is, so you've got, I need to keep shifting this thing around. So you have, so you've got black holes in a mass from about 1 billion solar masses to 10 to the 12 solar masses. So clearly, these are not associated with stars. They couldn't be formed in the evolution of stars. And one must have separate formation mechanisms which are linked to galaxies. These supermassive black holes are typically found at the centers of galaxies. Then there could be some isolated ones, we don't know about those, but they are found in the centers of galaxies. So what I will do is that I at some point explain to you why people thought that there will be these supermassive black holes in galaxies, and then how do you detect them actually. how do you detect these black holes in the centers of galaxies and their various manifestations, right? So now I immediately jump to something which is called the no hair theorem for black holes. Because you see, as it turned out, black holes are extremely simple objects. And they really, you cannot believe how simple they are. The only observable property that a black hole can have are mass, spin, meaning angular momentum, and electric charge. So you'd say spin mass m, spin j, and electric charge q. But where would they get electric charge from? Because black holes actually are matter, they're forms of matter, and you know that matter in the large is always electrically neutral. Yeah, as many electrons as there are protons, and so they are not charged. So therefore, even though theoretically these black holes exist and their metric is known, we'll be concentrating entirely on mass and spin. Right? So then now the properties of the black holes are scale free. What do you mean by that? Is that you could have, let us say that you've got a black hole with zero spin. This is called a Schwarzschild black hole because it was Carl Schwarzschild who gave the exact solution of Einstein's theory, which corresponds to this black hole. So you've got mass, and whether you have a mass of, say, 1 solar mass or 10 solar masses or a billion solar masses, the geometry around these black holes will be exactly the same. Right? So there is, you could just scale up and down the mass line, and still you will have exactly the same properties. The Schwarzschild radius will increase in length. So a billion solar mass black hole will have its effect felt to a much greater extent than a 1 solar mass black hole. But the form of the geometry and the gravitational field will be exactly the same. So there's no theoretical limit to the mass you can have for a black hole, which is certainly not true with other species of astrophysical objects. For example, you take stars. So the sun is a very typical star with a mass. 1 solar mass is equal to 2 into 10 to the 33 grams. That's the mass of the sun. So you couldn't have stars which are much smaller than that, because when you go to about 0.1 solar mass, then it turns out that you no longer have sufficient temperature at the center of the object to start nuclear fusion. So you can't have a star, which is less than about 0.1 solar mass. Similarly, as you go towards higher and higher masses, the properties of the stars keep changing. Their age decreases very dramatically. They not age, their lifetime decreases very dramatically. And once you come to about 100 solar masses, it turns out that the radiation emitted by the stars is so much that the sun is simply blown apart. Okay, so therefore, you really can't have arbitrarily small or arbitrarily large masses. Or take galaxies. So you've got spiral galaxies and you've got elliptical galaxies, and the structures keep changing as the mass changes. So you have dwarf galaxies with about 1 billion solar masses or 100 million solar masses, and giant galaxies, and the properties are all quite different. So black holes are not like that. They're completely pristine. Given a mass, given a spin, and all properties are determined. So that is why I don't have to give you the theory of stellar mass black holes and the theory of supermassive black holes and so on. There's just the theory of black holes. That is a very, very important concept. Right, so now in astrophysics, you start showing marvelous pictures for the kind of objects that you are talking about. A picture of a black hole would be all black because there's no light which can escape from it. So if you have a black hole somewhere in the galaxy by itself, then you wouldn't be able to see it at all. You could only feel its effects. You could feel the gravitational field. And also, as a light ray passes close to the black hole, then it could be bent from its path. And therefore, you will get gravitational lensing. So these are the ways in which you could detect an isolated black hole in the galaxy or anywhere else in the universe. But otherwise, if you discount these effects, you will not see. There are no electromagnetic effects associated with the black hole. Right? But on the other hand, we do see them pretty well because when we are interacting with other objects. So this is a artist's impression of a stellar mass black hole, say 10, 15 solar mass black hole, which is a part of a binary system. The binary system consists of a black hole here at the center, and then there is a normal star close to it. And the star is so close that matter flows from the star down to the black hole. And because of the angular momentum, it does not fall in radially. It goes round and round and round, and it forms a disk. And then matter slowly seeps through the disk to the black hole, and that matter gets heated, and then and the disk gets heated, and you can see it all in the optical, in the X-rays, and so forth. So you get an X-ray binary. So the black hole reveals itself through an X-ray binary like this. On a different scale, when you have got 10 to the 9 solar mass black holes, then they are resident at the centers of galaxies. They are again fed matter, not in the manner in which the star was feeding matter to the black hole, but you could have whole stars coming close to the black hole, and the black hole just grabs them, tears them apart, and eats up all the matter. Right? And then you could again get an accretion disk, and then you got magnetic fields associated with it, and then you get jets going out of the black hole. It's not out of the black hole, but out of the event horizon of the black hole, and you get what is known as an active galactic nucleus. So these are really phenomenal objects, and the most extreme counterparts of these, extreme examples of these are the quasars, which appear like stars, okay, but which emit 10 to the 12, 10 to the 15 times the amount of light which is emitted by a star like the sun. Okay, because of the processes going on in the nucleus, which are to do with the presence of a supermassive black hole. So I will talk to you in the course of time about a supermassive black hole at the center of our own galaxy, and how extraordinarily beautiful, painstaking, and lengthy observations led to the establishment of a very massive object at the center of our galaxy, which we believe is a supermassive black hole. So that has more or less been accepted. And the two people who led the two different groups who independently worked on that problem got a Nobel Prize last year. And the third person to get the Nobel Prize was Roger Penrose, okay, for his work on the theory of black holes. So which means that the Nobel Committee at least has agreed that what is at the center of our galaxy is actually a supermassive black hole. But a black hole has many parts. It has got many different appearances, and all of which are false. Okay, in the sense that you can't really see a black hole at all. But here is what is called a Penrose diagram for a black hole. Okay, so this is a space-time around the black. It's a black hole and a white hole combined together. I'll explain that a little bit later in my talk. Okay, but these are the entire infinity, the infinite space which is surrounding the black hole, and in fact the white hole is in a finite region here using a device which is known as a conformal transformation. Okay, so you need to get into these devices in order to understand the geometry associated with the black hole. And here's a picture of Roger Penrose, who got the Nobel Prize. Okay, so now we come to the theory of black holes. Right, so as I said, first I'm going to do a little bit of Newtonian thing. Always in my calculations, wherever possible, I'll first introduce Newtonian concepts. Okay, and then I go along and then come to the general relativistic, corresponding general relativistic concept. Right, so Newtonian black holes. So you start with Newton's theory. You all done that for many years right now, however young you are. And so you've got F is equal to minus G M1 M2 by R square. Everyone knows these two equations. This equation and E is equal to MC square. Right? So you also know the concept of a black hole. So you're somebody throwing a ball in a transformation from one format to another. It's got converted from a circle to oval. I didn't notice it earlier. So you throw up a ball here, and depending upon how fast you throw up the ball, the higher and higher it goes. And if you throw it up with escape velocity, it just escapes to infinity. Right? So, so what are the calculations? So, I got half mv squared by the gm by r is equal to 0. There should be a small m here which is missing. So kinetic energy plus potential energy is equal to 0, where when it goes right to the top, the energy is conserved. And then you have, therefore, V is equal to square root of 2 gm by r. And if you put in these, if you put in these numbers here, then the mass of the Earth and the radius of the Earth and so forth, then you will come to escape velocity of 11.2 kilometers per second. Right, so you're all completely familiar with this concept. Now, supposing instead of the Earth, I got a more massive sphere with the same radius, the density will be with a smaller radius. I'm sorry, the same radius but with larger mass. The density, of course, will be much greater. The gravitational field will be stronger, and therefore the escape velocity will be larger. Or keep the same mass, reduce the radius, you get the same effect. Increase one, decrease the other, doesn't matter. So you can go on doing that until the speed matches the speed of light. At which point a light ray will not be able to escape from the force of the gravitational field of the Earth. Now here, of course, I'm assuming that a light ray will behave same as a particle. Newton never said anything about light rays, but we know in general relativity that is indeed so. So, because now in special relativity, nothing can travel faster than light. In Newton's theory, that is not true at all. What you could do, for example, is that you could sit on a rocket and then shine up a light upwards, and then relative to the Earth, it will be traveling with the speed of the light plus the rocket velocity. And so, therefore, when this calculation doesn't worry anybody. In particular, the two people first thought about it. One was John Michel, and he said that in 1784, he said that a body with the same density as the Sun, but 500 times larger in radius, so r cube times greater mass, would not allow light to escape from it. And then, much more famous gentleman, Laplace, about whom you would have heard in your mathematics courses, mathematical physics courses, and he said that it is therefore possible that the greatest luminous bodies in the universe are on this very account invisible. Right? So what account? Whatever. Meaning that light cannot escape from it, and so these bodies will be invisible. But he was not worried at all because there was nothing sacred about the speed of light. Right? So that thing we come to when we go to general relativity. The problems associated with the limitation of the speed of light. And so now we have come to black holes in general relativity. So first, a little bit, just two statements about special relativity. All of you would have studied the special theory of relativity. And so the two principles, there are special frames of reference called inertial frames. So you all know what inertial frames mean. And then the laws of physics are the same form in all the inertial frames. So I sit on one inertial frame and I work out my physics. And then I sit on the other inertial frame and work out the physics. It will be the same. Now this was first discovered, understood by Galileo Galilei more than 400 years ago. Right? So that was the principle of relativity that Einstein refers to. So Galileo provided the inspiration for both the special theory of relativity as well as the general theory of relativity, because here he talks about inertial frames, and then Galileo's understanding of the equivalence principle, that the inertial mass is equal to gravitational mass, is what set off Einstein towards the correct solution to combining gravity and special relativity. And so, and what are the consequences of these two things is that the speed of light is the same in all inertial frames. Simultaneity is relative. You can work out the Lorentz transformations. You can got E is equal to mc square and particle mass increasing with velocity and so on and so forth. Right. So, so here you have got. Sorry, I have to move this thing around. All right. I mean, I can just guess what is behind it. So here are the Lorentz transformation equations. But what I would like to draw your attention today is to the metric of the flat spacetime. So we know that in three-dimensional normal geometry, this quantity is a constant. I mean, if you rotate coordinates, it remains the same. So similarly, this quantity ds square is equal to minus dt square uh, plus dx square plus dy square plus dz square, as you all know, is a Lorentz invariant. Okay, meaning that if you evaluate, you have two events which are separated by dt and dx dy dz, and you evaluate this one, and then you go to other frame of reference, initial frame of reference, and again get the corresponding intervals there. You will find ds square is an invariant. Okay, is the same, and that follows from the Lorentz transformations. On the other hand, you could make the hypothesis that when you go from an initial frame transformation, it was leaving this element invariant, and then you could derive the Lorentz transformations. So now, supposing instead of using x, y, z coordinates, I use r, theta, phi, spherical polar coordinates, and then so this is the line element. Right. So now it appears to be curved because here you see that all the things are constant, coefficients are constant, and which means that space-time is flat. And space-time is flat, meaning what? It behaves in the way you intuitively expect it to behave. The sum of the three angles of a triangle is equal to 180 degrees, and parallel lines don't meet, and so on. And so now here, it is not obvious that space-time is not curved, and in fact, you could have this line element on the surface of a sphere, which is not curved. But here in four-dimensional space-time, so this is simply a transformation. You can transform from x, y, z to r, theta, phi. And any problems with this coordinate system, this line element, are problems with the coordinate system rather than with the structure of space-time itself. Now, if I ask you, what is the definition of R? What do you mean by R? Okay, so you'll say that if I consider the locus of points on which R is a constant, then what do I get? I get a sphere. That I get the surface of the sphere. So I could fill that surface in and get a three-dimensional object. Otherwise, I have got a two-dimensional object in three-dimensional space. So now, by definition, the distance from the center to the surface of the sphere is R. Right? So that is the meaning of R. But R also has got another meaning, is that if I measure the area of a sphere and then divide it by 4 pi, divided the area by 4 pi and take the square root, then I'll get R. So that is the meaning associated with it. Okay, so R square is proportional to the area of a sphere. You could also say that it is proportional to the volume of a filled sphere and so forth. And so here, so please, I'm stressing on this because I'm going to be using these concepts in general relativity. All right. Now, the fact that this is invariant produces this light cone. You're all familiar with what is the meaning of a light cone. Is that if I'm sitting here and there's an event A, what is that event A? Is that I shine a torch. So as I shine the torch in a particular direction, the ray of light will go in that direction. This is X and this is the time. So if I got X and Y, then instead of getting a cone like this, I get a three-dimensional cone. Right? But actually, there's a similar structure in special relativity. Actually, the three dimensions of space and one dimension of time, which would mean that it's a cone in four-dimensional space-time. So now, all the light rays which go out from this event, they'll be along these two boundaries. All time-like lines, okay, meaning that things which are traveling slower than light, all material particles, all particles which have mass, would be contained in this future light cone. So I could, sitting here, I could affect something which is happening here. Right? So if you are sitting there and then you want to shine the torch, I can send a signal to you from there to there at speed less than the speed of light and say that no, please don't shine the torch. Or if you are sitting here, I can send you a signal using an electromagnetic ray. But if you are sitting here, then there is absolutely no way in which I can communicate with you within the time available. And so similarly, anything which is in my past can affect me from inside this light cone. Because if you're sitting here, I'm sitting here, you could send a particle which travels with speed less than light and reach me by this event, right? Or you could reach me along the borders of the light cone. So now what happens is that the structure of the light cone is invariant. The fact that this line element is invariant means the structure of the light cone is invariant. So you go to other frame of reference, initial frame, everything will get cockeyed. Okay, meaning that all the things change. But what is in the past will remain in my past. What is in the future will remain in my future. So the light cone is invariant. Okay, but please understand that when I got X and Y and T, or X, Y, Z and T, these light cones are these all straight lines in space. Okay, and the light cone is just pointing upwards because the time axis, okay, the axis of the light cone is by definition time axis. So why am I belaboring such a simple point? That is simply because when you actually go to general relativity, you will find that this cone could actually lie on its side so that the space and time axis get flipped. All right, so now we come to general theory of relativity, which is a theory of space-time structure and of gravity, the two taken together. So, in special relativity, there are privileged frames of reference which are known as inertial frames. In general relativity, there are no privileged frame of reference. Any set of clocks, any set of axes, whatever you want to do is the same. The theory will remain, it will maintain its physics. The physics will be completely the same, regardless of which frame of reference you use. In particular, I may be sitting here, I may be sitting in space in an inertial frame. You may be accelerated, but your physics will be same as my physics. Okay, then the principle here is that the matter, by matter I mean matter and energy, they curve space-time. And so that is the effect of matter on space-time. And then particles move along the geodesics of the space-time. So what are geodesics? So we know in special relativity that particles move along straight line if there's no force acting on them. So here, the presence of, there is no gravitational field at all. Right? So gravitation is no longer a force. Gravitation is just a manifestation of the curvature of space-time. So since gravitation, there is no force, unless there is electromagnetism or strong interaction or whatever, there is no force. Particles are always moving along the straight lines, the paths of least action of the curved geometry. And those are known as geodesics. Right? So now, what are the equations? There are two sets of equations that you have here in the general theory of relativity. The first set of equations, which are called the field equations. And what carries information about the geometry? It is the metric tensor. What do you mean by the metric tensor? Just go back to special relativity. So this was the metric of flat spacetime. And so now this is also the metric of flat spacetime. Even though the coefficients are not constant, if you calculate the curvature of the spacetime, you find that it is zero. And so, whereas the coefficients are known as the metric tensor. And general relativity allows for metric tensors which result in curvature of spacetime. Okay, so these are very complicated. There are 16 equations, but only 10 are independent. And this is the matter which is present. And that is, and then you have to take that as the source term, and then you have got to calculate what is the gravitational field. But this is a non-linear theory. So if there are two particles interacting with each other, then there is gravitational energy corresponding to that interaction. That gravitational energy also becomes a source for the field. Right? So unlike in electromagnetism, where charges and currents produce electromagnetic fields, but the electromagnetic fields themselves are not their own sources. But the electromagnetic fields can very well be the sources of gravitational fields. And this is the equation of geodesic deviation. Xi is the coordinate, S is the invariant line element, Ui is the phore velocity. I'm sure you have seen phore velocity in special relativity. And so this is, if this is the velocity, then this is the acceleration curve. So acceleration, MA is equal to minus GMM by R square. Right, so this is your M has been taken away, but this is your acceleration and this is your force. But that is not the interpretation. The interpretation is that space-time is curved. The curvature manifests itself through these Christoffel signals, okay, and particles are moving along geodesics of these signals. Right, so so then what do you mean? So these are straight lines. So you'll say the Earth is going around the sun. So we know that the orbit is elliptical. So now please tell me, what do you mean by saying that it is moving along a geodesic? That's very easy to answer. Don't look at the orbit in space. That is a closed orbit. Look at the orbit in space-time. So mercifully, the orbit of Earth around the sun is two-dimensional mostly. Right? So let us take it to be exactly two-dimensional. Then take a third dimension, which is the time axis. So then you see that it is going up in a spiral. And it appears to you to be a spiral. But when you take into account the curvature of space-time, so you will find that it is actually a geodesic. All right. Now, Einstein gave his theory in 1915. Shall I stop here now for you to ask questions? Does anybody have any questions at this stage? Yeah, there is one here, Unique Sengupta or Unique Sengupta. Then,
hello, sir. Am I audible?
Yeah, you are.
Thank you, sir. So my question is regarding the first part of your talk when you were discussing about the primordial black holes. You said the primordial black holes, absolutely there can't be an astrophysical force because
I'm not going to answer any of those questions now because they will come later in the talk. That was just a total introduction. Okay?
Okay, sir. Then I'll proceed.
Yeah.
Thank you, sir.
Astha Chaturvedi.
Am I audible, sir?
Yes, please.
Yes, sir. Is there anything like relativistic mass of black hole?
Relativistic mass, no, they're just a mass of the black hole. Okay? So, so if a black hole moves at a high speed, then obviously the mass will be different from what it is when it is static, but otherwise just a mass.
So, what's the difference that we can detect when the black hole is moving at a very high speed?
Yeah. You'll have to take into account all the difference.
Okay. And sir, about the frame of reference, I have heard it like many times that CMB is the kind of absolute frame that we use for the observation. So can we say that it is a privileged one?
Which one?
Cosmic microwave background.
No, it is not. You could have it, but it is clearly not a privileged frame as such. It just you ask this question in cosmology. Okay? When they talk to you about microwave background, just ask them this question.
Okay, sure.
So what I suggest is that please keep your questions confined to actually what I am saying, because that is complicated enough, and then we can have general questions at the end of the talks. Okay?
Sure, sir.
All right. So shall I go ahead now? Okay. So now Einstein gave his theory in 1915, and then when he gave the theory, he did not have any exact solutions of the theory. He got approximate solutions on the basis of which he made a prediction. Okay, he made three predictions. One, that there will be bending in the direction of light because of the gravitational field of an object. He was already aware of that from the equivalence principle, but he gave the exact calculation for it. And then he talked about the redshift of light. So he said that as a beam of light moves against a gravitational field, it will be redshifted. If it moves into a gravitational field, it will be blue shifted. And the third one was he said that he considered the motion of Mercury around the sun, and he showed that the small discrepancy in its object in the orbit could be explained because of general relativity. This last one, I'll come to it again later. Okay, but then in 1916, that's a year, or probably less than a year after Einstein announced his theory, Carl Schwarzschild, who was a very great astrophysicist, he gave the first exact solution of Einstein's theory, and that solution corresponded to a point mass. So let us say that if I got a point mass in Newton's theory with a mass m, then at a distance L, at distance r from it, the gravitational field would be minus g m by r. That would be the gravitational potential. And the gravitational field, which is the force per unit mass, would be minus g m by r square. And you understand that the point mass has no structure, and therefore the space around the point mass would be spherically symmetric. The force around the point mass is spherically symmetric. It doesn't matter in which direction you are, the force will be exactly the same providing the distance is the same. So the solution which Schwarzschild considered was you take a point mass and which has no structure, nothing, no property other than its mass. And therefore he argued that the curved geometry of space-time would be spherically symmetric. And then he derived the solution. And this is not the coordinates that he used, but this is the very obvious coordinates that we have here. And so what you have here, so you've got 1 minus 2 m by r dt square, 1 minus 2 m by r minus raised to 1 dr square plus r square d theta square plus sin square theta d phi square. So now, first of all, you must understand that I'm using the units c is equal to 1 and g is equal to 1. Sometimes I plug in these things for convenience. But so if you want m in physical units, space in space units, time in time units, then you would say 2m will be replaced by 2gm by c square. Right? So now here I got g is equal to 1 and c is equal to 1. Now, first of all, let us look at this part of the geometry. So it is exactly the same, which you get in the space in the line element of special relativity. I explained that to you already. So what is the interpretation of R here? Is that if in this curved space-time, I draw a surface with constant R, then I'll call it a two-sphere. Right? So then the two-dimensional sphere. And then this sphere has a certain area. And I can actually measure the area by taking a meter rod and putting it there and measuring the area. So if you take the area and divide it by 4 pi and take the square root, then the answer will be R. Right? So R, if I say that the space, this surface has a radius of R, I'm also saying in this geometry that the area of the surface is 4 pi R square. So you'll say, what else is new? You already heard this before. But does it mean that R is the distance from the center to the to the surface? That is not true. Why is it not true? Because consider a point on the surface. So here you've got fixed theta and phi, and then you try to join 0 to R. So you'll actually be varying the dr, right? You'll be varying the dr from 0 to the surface of the sphere. And then when you try to integrate over that, you see that you are getting in this particular part here because space-time is not flat. And therefore, the distance that you get between the center and the sphere will not be equal to the value of R between the center and the sphere. So which is a demonstration of the fact that space-time is curved. Moreover, this coefficient is also not constant, means that the curvature also goes to the time part of the axis. And so now given this metric, everything about the geometry is known. You can do any calculation you want. You can take the orbit of planets around the sun, you can take bending of light, you can do everything. Now you must understand that this was done in 1916, which was plumb in the middle of the First World War, and Karl Schwarzschild was in the battle and he died there. And so that is the unfortunate part because he had done such brilliant work. He was young, he would have done so much more afterwards. But I had the great good privilege of meeting, even at my age, I would be too young to have met Karl Schwarzschild. But I met his son, Martin Schwarzschild, who himself was a great, when I met him when I was a postdoc, he was a very senior astrophysicist who should travel from Princeton to Cambridge where I was. Okay, now, what is amazing about, what is the new thing about this solution is that it has got an event horizon. So you have got, which makes it different from a Newtonian black hole. So this is called a black hole solution. So let us first understand. So we'll quickly work on this now. But look at this. First of all, when R is equal to 0, you are getting this coefficient blowing up. So there's going to be a big problem. But you see, when R is equal to 2m, then is R is equal to 2gm by c square. 2gm by c square is called the Schwarzschild radius. So when R is equal to Schwarzschild radius, this becomes infinitely large. And when it becomes infinitely large, you find that, oh my God, there's a problem there. It turns out that there is no problem. Because space-time curvature remains finite at that point. Where R is equal to 0, there's a particle sitting, it has infinite density, it's a physical singularity, but you'll also find that it is a geometric singularity, meaning that the curvature of space-time at R is equal to 0 is infinitely large. So which means that you the very concept of space-time structure is no longer tenable. That is a problem with the black hole. Now to understand, how do you go about establishing that at R is equal to Tm, 2m, there is no problem. So this is what we are doing. You see that I told you that you could use any coordinate systems that you pleased in general relativity. So there are any number of coordinate systems available which reveal to you different aspects of the black hole geometry. But here, look at these coordinates which are known as the Eddington-Finkelstein coordinates. Okay, so so you got T and R, you leave theta and phi unchanged, and you define a coordinate V by this expression. Okay, and then you just put that in. And then what will you get? You'll get ds square is equal to this one here, and 2 dV by dr, and the same line element here. So 1 minus 2 m by r raised to minus 1 no longer is there. V is your time coordinate. Okay, and that singularity at the Schwarzschild radius has disappeared. So which is just a demonstration that it is not a real singularity at that point. Okay, so compare it with this one. Sorry, I forgot to put on this line element. We could do the comparison. So now, what happens in the Eddington-Finkelstein coordinates? I'm going to do that very, very simply. Consider a radial light ray, which means, what do you mean by radial light ray? Let's say that I shine a torch from the center of the earth down the surface, then it will move radially. Right? So there, d theta is equal to 0, d phi is equal to 0. So only dv and dr. So and then you know that along the light ray, ds square is equal to 0 because it moves along null trajectories. So put ds square is equal to 0, and then you will get this quantity to be 0. And what are the solutions possible for this equation? One is that dv is equal to 0 clearly. Is one solution. So which means v is equal to constant. So in this coordinate system, v is equal to constant represents light rays. And then here, the other solution is this expression which I got here. So now on the right, you'll find a diagram. And I'm sorry, this diagram is from Hartle's book. There are so many diagrams I could have lifted from the internet, but this diagram is absolutely the best. So even though I couldn't reproduce it properly, it is here. And it would be too much trouble for me to draw it myself with the mathematics in. So you see that here you've got the singularity at r is equal to 0. And this is the r is equal to 2m. And this is a coordinate, this coordinate here, t is on this axis and r on the other axis. And v is equal to constant, r the light rays. You can see that. And where the other light ray is given by this particular equation, which is the curved trajectory here. So this is simply a simple demonstration of the fact that the singularity at r is equal to 2m, which appears in the standard Schwarzschild solution, is not a real singularity at all. Okay, and in fact, it reveals to you beautiful things about the space-time. So now you remember the light cone of special. I should have said one more thing here. So just look at the light cones here. You see one arm of the light cone is v is equal to constant, and other arm. And then you see that as you move inwards, the light cones actually are bending. They are becoming narrower. They are no longer maintain their shape and their direction as they do in flat space-time. So here, this is a purely schematic, of course. So you've got R and T. So if you have a light cone here, then you will find far from it that it will be like a light cone in flat spacetime, because as R increases, becomes very large, the Schwarzschild solution reduces to the usual flat space solution. So light cone, but as you go closer and closer, the light cone actually starts bending, right? And it bends here. And when you come to R is equal to the Schwarzschild radius, you'll see that one arm of the light cone is actually along the Schwarzschild radius. R is the constant. What it means is that, and I'll show it to you later, is that if you go to R is equal to constant and shine a light ray, a torch, it'll get stuck to R is equal to constant. It'll just go round and round and round, and you get what is known as a photon sphere. Whereas the entire future light cone is bending inwards. So once you are inside, either at this point I shine a torch, if I do it along R is equal to constant, it'll just get stuck to that radius. Whereas if it is in the forward light cone, it cannot come out at all. It must go towards R decreasing. And finally, it ends up here. Right? So therefore, that is the reason why this is known as an event horizon. It is known as an event horizon because whichever way you shine you shine your torch, the light will always end up at the singularity. And because everything else, all massive particles must be within the future light cone, they'll go to singularity. There is no such problem in the past, meaning that if you throw in the ball here, it will go into the past light cone and cross and go to the singularity. But if you throw a ball from here, it cannot go out. It must go towards the singularity completely. So this is a very vivid demonstration of the fact that the event horizon, that R is equal to RS, the sphere with R is equal to RS, is a one-way membrane. Nothing can go from inside to the outside, but things can go from the outside to the inside. Right. So what have we learned here is that if I have a point mass, then at the point mass I have a singularity, and this is not only like a Newtonian singularity of space, but it's also a singularity of space-time. Okay, and then this is the event horizon with Schwarzschild radius is equal to 2gm by c squared. That's right. So what is the scale of this one? Just look at this equation. Rs is equal to 2 into 10 to the 8 m upon 10 to the 8 solar masses kilometers. What does it mean? Is that if the mass of the black hole is 100 billion times the mass of the sun, then the Schwarzschild radius will be 300 billion kilometers. But if you've got a black hole with the mass of the sun, then m is equal to, this is 1, so you 10 to the minus 8, which cancels this 10 to the 8, and you get the Schwarzschild radius to be 3 kilometers. Right, so that is the 2.95 or whatever kilometers is the Schwarzschild radius of our sun. Okay, and in terms of parsec, so you don't unit parsec, I'm sure. In terms of parsec, it is 10 to the minus 5 m by m solar parsec. This will be of relevance when we talk about the black hole with the center of a galaxy. So now, given all this, what happens? What about the motion of particles around the black hole? So I'm going to take you through that. Where there's going to, I believe that I have another 10 minutes or so here. Let's see how much progress we can make there. So now just let us look at what is known by a conic section. Right? So you know that the Keplerian orbits are conic sections. So which means that the orbit around the Earth around the sun is an ellipse. If you neglect the influence of all the other planets, which we will. Right? So then, when a comet comes in from a distance and goes back, it's on a parabolic or a hyperbolic orbit, depending upon its velocity at infinity. So what is the general conic section? What is the equation of thing? That P by R is equal to 1 plus E cos phi, where E is the ellipticity. Okay, and these orbits are all two-dimensional. So theta is equal to pi by 2. And so pi changes. And P is the semi-lattice vector. So if E is equal to 0, R is a constant, because all the other quantities are constant, P is a constant. And therefore, you will get, if R is equal to constant, you get a circle. If E is equal to 1, no, E is less than 1, then you will get an ellipse. Okay? For E is equal to 1, you get a parabola. And then for E is greater than 1, you get a hyperbola. So hyperbola occurs when the particle velocity is non-zero at infinity. But if a thing starts with zero velocity at infinity and falls into the earth, into the sun under the influence of gravity, sun's gravity, then it would be a parabola. Right? So now we know the answer, but how do you derive them? So let me see here. So you start with a Lagrangian, and the Lagrangian is equal to the kinetic energy minus the potential energy. And so you have got, so this is the kinetic energy is equal to r dot square plus r square phi dot square. So this is just a velocity in the two-dimensional surface that it is moving. And VR, VR is equal to here G M by R. And so now you're going to, if you look at this, this is the Lagrangian is independent of phi, so which would mean that the angular momentum m r square phi dot square is equal to 0. Also, the Lagrangian is time independent, which would mean that the energy is conserved. And what is the energy? It is equal to the kinetic energy plus the potential energy. But the potential energy term is negative, so you're going to minus sign here. Minus Gmm by R. Right? So now what I can do, and this is very important for my future, for the next slide, is that I can take out this term and add it to this term. So what do I get? E is equal to half m r dot square by the G m by R plus L square by 2 m r square. Right, so so now I can write E. E is the energy of the particle. I take this script E to be E by m. I'll call this also E. Is E by m. Script angular momentum is L by m. Angular moments per unit mass and energy per unit mass. So then this equation can be written as E is equal to half r dot square plus V effective. V effective is the effective potential. And what is this equal to? Minus G m by R plus L square by 2R square. So you know that when the potential is negative, then it is an attractive force. When the potential is positive, it is the repulsive force. So if you are in front of me here in this room, I would ask me where is the repulsion coming from, and I'm sure all of you would have answered in one voice that it is because of the centrifugal force, which is a pseudo force. It's not a real force. So it's centrifugal force. So the effective potential is made up of the gravitational attraction plus the centrifugal force. Right? So you don't want this one. So now, now we have got a nice diagram here. So here you have got V effective is minus Gm by R square plus L square by 2R square. So this is the energy axis. Okay, and this is R. So now let us say that I want to plot this quantity. What will happen is that as R goes to infinity, this quantity will be 0. So a particle starts approaching the center, then 0, 0, 0, 0, 0 until the effect of this term is felt. And because this is an attractive force, the potential will keep decreasing. Right? And as it goes inwards, this term is becoming more and more negative. This term is becoming more and more positive. But please see, this is proportional to 1 upon R, this is proportional to 1 upon R square. So regardless, if L is equal to 0, there's no well at all, the particle just flat falls. It is only this kind of a thing here. Right? Whereas if you get a rectangular hyperbola, then if the smallest amount of angular momentum in Newtonian dynamics will get at sufficiently small r, this term will always dominate, regardless of how small the angular momentum is. And then you go down, and then you get a minimum here. I can't see it because this is panel coming here. Yeah. So then you go up and you start going up, and the fact that this is going up means it's a repulsive force, right? So you get this particular gravitational potential then. Now, supposing I throw a particle from infinity, and so when it's at infinity, uh, with a certain energy, half r dot square plus v, at infinity this is zero, so this is not zero. So there's a straight line here. This is not the movement of the particle. This is just the line in energy space. This is the energy axis, the right one, the top axis. So you get this is a fixed energy. So how is the particle moving? You could move radially, but if you are moving with any angular momentum, the particle has angular momentum, because L is not equal to zero. So then what happens is that the particle, it is like a comet. It comes in as the R is decreasing, the angle will be increasing. And therefore, it just goes around, it just comes from far, comes close to the sun. There is a periastron, and it again goes back to infinity. And this is the turning point. This is the periastron. It just comes from outside, goes back. But it is not linear motion like this. It's a hyperbola. On the other hand, let us suppose that you have got a particle which energy is negative. The total energy is negative. So then you couldn't take it to infinity. Because if you took it to infinity, no, the total energy at infinity cannot be negative. Because there's only this part which will exist. This part which will exist. And kinetic energy can't be negative. So if you have got a particle of negative energy, then it must be bound. It must be bound with the orbit. Okay, so it must be bound in a well. And you've got this orbit here. So you see that the particle will go here. It means it is going around the sun. And here it reaches the periastron. It turns back, which means that it is going. And what is the shape of this orbit? Because R is changing. Okay, so but it's a closed orbit. And so anybody, you'll all remember from your lessons that this orbit will be an ellipse like this. So we have explained Keplerian orbits. Right, so this is a hyperbolic orbit. If you came along the red axis, then it will be a parabolic orbit. And if you came on a hyperbolic orbit and I just take away the energy from this, it will fall inside and it will become an elliptical orbit. And if you are bottom of the potential, what will happen? So if you are here at the bottom of the potential, then your energy is a minimum. You're just stuck there, and R is a constant. So which means that you'll be moving in a circle, not an ellipse. It's an ellipse with zero ellipticity. So that you'll be moving in a circle. I'm quite sure that you have studied all this before, and completely this explanation is very straightforward. And what I'm going to do now in the remaining 5 minutes for me is to go to the Schwarzschild effective potential. And so what did we do here? We have got the energy per unit mass in Newton's theory, in Newtonian dynamics. This is the kinetic energy plus this is the effective potential. And effective potential is given like this. So if you go through all the general relativistic calculations, you look at the geodesic and you do it. So when I first did this, getting the geodesics was very difficult because you have to evaluate all the Christoffel symbols. And the Christoffel symbols, there were 3 bases to them. So 4 into 4 into 4, 64 Christoffel symbols for the trajectory. But then quite soon, just a year or so after when I was in graduate school, a new book was published called Gravitation by Meissner, Thorne, and Wheeler. Okay, and there they introduced differential topology, differential geometry. And if you use those methods, which I taught myself, then when you calculate the Christoffel symbols, because of symmetries, many of them turn out to be zero. Now here, when you do the calculation, using the new method, 10 new methods, I'm talking of 30 years ago, 40 years ago, then the zero ones never appear in the calculation. Anyhow, so you see that the general relativistic expression corresponding to this is here. So you see how similar it is. It's exactly the same, except that this t here, coordinate time, is replaced by the proper time theta. No worries. And V effective is this term. This term is the Newtonian gravitational attraction. This is the centrifugal force. And this one is the pure general relativistic term. And this goes as R, this goes as R squared, this goes as R cubed. So which means that when you move sufficiently close to the black hole, then you will, then the black hole takes over. So I get asked this question all the time. I was first asked it when I was 20 years old. I'm sure that if I live up to 100, I'll be asked at that time also. So why doesn't the Earth, why don't you fall into a black hole? The answer is very simple. If you try to fall into a black hole and you are far from the black hole, then it is these two terms will dominate. And as you move, because of your angular momentum, the centrifugal force keeps you from falling into the black hole. The centrifugal force keeps the Earth from falling into the sun. But the beauty of the black hole is that regardless of your L square, as you decrease R sufficiently, the black hole is going to swallow you. So that is what this term means. And now, what is E? So here E is energy. So just because I have written this thing as E, does it also is the energy? It is not. It is close to energy, but not quite energy. Let's see what I mean, and then I'll stop. So you see that here, if you actually look at general relativity, and you remember I told you that energy was conserved in Newtonian dynamics because the Lagrangian is independent of the time coordinate. Similarly, the Schwarzschild metric is independent of the time coordinate. And therefore, you can say that that energy is conserved. And it is this one is the expression for energy. And here I put back the mass. And then, so this expression that you evaluate, which we are not going to do here, is turned out to be this. So this is the energy. So the energy per unit mass is this. So there is a gravitational term coming in. And if I take R to infinity, then this term is going to go to 1. And so the energy will be ME. This quantity E is ME is equal to M upon square root of 1 minus V square. And what is this? This is just the particle energy of the particle moving with the speed V. That is why this E here, that we justify the term E as energy for E, which is introduced in this complicated fashion. Right. So then, what happens to E? So E is equal to this one, 1 upon square root of 1 minus V square, which is for V is much smaller than 1, which is V is much smaller than the speed of light. Then E goes to 1 plus V square upon 2. Right. So which means that as V is really goes to 0, E goes to 1. So now let us evaluate this E here with this quantity, which is equal to 1 plus E to 1 minus E. This is approximately equal to 2. And so this will be 1, and so I get V square by 2. So you see that this quantity here also at infinite distance from the black hole becomes the kinetic energy. Right? So therefore, why am I justifying all this? It is because the expressions look similar to this expression, but you should not take them blindly. There are all kinds of hidden things involved in them which lead to completely new phenomena. Okay, I've come to the end of my time. All right, so I'll stop here. So next time, I'll show you what are the particle trajectories. Then what kind of wells do we get here? And you'll find that you don't get stable orbits for all values of R. And then the trajectories of light. I would have very much liked to finish this today, but there's no time for it. So let's do it tomorrow. So please send these messages to me if you find that my lecture has been either too fast or too slow or not clear at all or whatever, so that I can try to improve myself. Yeah, Shriya.
Good afternoon, sir. Am I audible?
Yeah, you are audible.
Sir, I just wanted to ask about the physical significance of event horizon. Sir, can you please explain it once again? What actually is event horizon?
Event horizon. Yeah. So you see, So you understood that there's a black hole with a mass m, right? So there is a radius corresponding to that, which is known as the Schwarzschild radius, which is equal to 2gm by c square. So if you have got a if you've got a black hole of the mass of the sun, it will be 3 kilometers. So now if you approach, so long as you are outside this 3 kilometer surface, it is not a real surface, it's the imaginary surface. So long as you are at a greater distance from a black hole than 3 kilometers, then solar mass black hole than 3 kilometers, then you can go wherever you like. You can go to Mars, you can go to Jupiter, you can go anywhere. But on the other hand, if you approach this black hole, solar mass black hole, to within 3 kilometers, you go inside 3 kilometers, then you say, oh my God, I'm trapped. Because in order to move back outside of the Schwarzschild radius, you require infinite energy, which you don't have. And so therefore, you can go through the Schwarzschild surface, event horizon, but you cannot come out of the event horizon. So which means that the black hole is completely opaque. You can never look into it. You can never see what anything coming from outside. So that is why it is known as an event horizon.
So, sir, as we are outside of it, so from inside of the black hole, from the event horizon, the things can't come out. So, how do we at first came to know that this is the event horizon outside of this?
You come to know that you come to know that because of the way particle trajectories move. That it's a very important question that you're asking. Have you seen the image of the black hole? The first image of the black hole?
Yes.
It was published in 2019. Okay, I'll tell you what. Let me go somewhere ahead in my lectures, and then I will show you an image of the black hole, and I'll tell you what happens to light rays and how you know that there is a black hole. Okay? I need to introduce some more concepts to that. Okay, there are too many questions, but okay, Anushka Tilekar.
Yes, hello, sir.
Yeah,
Am
I
I
can hear
audible?
you. Yeah.
Yes, sir, can you please suggest any good reference books for what we studied today?
I told you that right at the beginning of my lecture. So there's a book called Gravity by James Hartle.
And
Okay.
any more?
Yeah, there are actually several. See, the thing to do is that if you have access to you'll probably have access to just go to the IUCAA webpage, go to the IUCAA library, okay, and then you look at books on gravity, or you could even do that on the internet, okay. But what I will try to do is I'll just get together 4 or 5 names of books and authors and so on, and I'll send them out.
Yes, sure, sir.
Yeah.
Thank you.
Okay. Who else now? Somebody who has not asked a question. Ajit Talukdar.
Am I audible, sir?
Yes, please.
Sir, in the potential term, there was a repulsive term we have seen.
Yes.
So basically, whenever something is rotating around a black hole, so is that the repulsive term responsible for sometimes we see that the objects are thrown away from the the boundary of the black hole? Is it the reason, sir?
See, don't worry about the black hole. Just look at the Earth going around the sun. Now, just imagine for a moment that let's take a body of the mass of the Earth and let us hold it and leave it near the sun. It will just fall into the sun, right? So why is it the Earth not falling into the sun? That is because it is going in a circle. And then, so what happens is that if I'm a point A in the orbit, then the velocity of the orbit will be such that I tend to move along the tangent to the circle at that point. Assume that it's moving in a circle, tangent to the circle at that point. But as I try to move along the tangent, the gravitational field will pull me inside. So the direction of the tangent changes. So if I go on looking at that, then you'll see that because of the velocity that I have, the velocity which is perpendicular to if I take a line drawing the center to the particle, and then the velocity perpendicular to that is not affected. The velocity which is along the radial line, you get pulled inside. So generally what happens therefore is that if you do this analysis, that you will get a circle, the particle going around in a circle. But you could also say that if I go to the frame of reference of the particle, then in that frame of reference, the particle is not moving at all. I'm sitting on the earth. I'm not falling onto the sun. Let's say, then what do I say is the reason? The reason is that I will say that there is a force acting inwards toward the sun on the earth, but also there is a force acting outwards, which I will call the centrifugal force. But you know that there is no centrifugal force. It is just an artifact. So the angular momentum term is that part, which saves you from falling into the sun. Similarly, now remove the sun, put a black hole. I showed you that you got exactly the same analytical expressions. But in general relativity, you will not talk in terms of forces. You will only talk in terms of potentials. And then you know that one potential has got a negative thing, the other potential has got a positive gradient, and therefore the net result is the well in which you are moving. Just learn to interpret it like that.
Thank you, sir. Sir, basically, I have another question. Sir, it's about space-time. Sir, how can we analogically imagine what space-time is? Sir, is it like something spatial, a three-dimensional object which is evolving in time, or is it just like a completely abstract idea?
So it is like this. You take yourself, right? So you are evolving in time, right? You're young and then you'll soon become old. And you are evolving in time. But you will look at you as an inert particle. At every point, you are somewhere in space, right? And then as you move, as time passes, okay, then let's say, are you from Assam?
Yes, sir.
Yeah. So are you in Guwahati?
No, sir. I am nearby.
Yeah. All right. So you are in your own place, and if you sit in your own home, like I'm sitting in my own home, I'm sitting on a chair, I'm not moving. So which means I'm static, but I'm static in space. In space time, I'm continuously moving along the time axis. So you see that? Now, if I get up, and now, so you are also presumably sitting on a chair there. So if you draw a coordinate system there, three-dimensional coordinate system with you at the center, then you'll be moving continuously along the time axis. But if you now actually get up and start walking, then you're not moving. So your motion along the time axis remains the same, but now you're also moving along the other axis. And the net vector, okay, is what you'll be moving along at any given point. Right? So now this is in four-dimensional space-time. So whether you can call it an abstraction or you can call it whatever, but the fact is that the manifest world, the real world, is a manifestation of this mathematical idea. So where the mathematics stops and where the physics begins is for you to decide. Right? But the point is that the curvature that we talk about is seen in the equations. The curvature that we feel is in the gravitational field. Right?
Yes, sir. Thank you, sir.
All right, I think we should stop there because otherwise you'll screw up the entire timetable. And I'll see you tomorrow again. So, can somebody switch on their mic and say whether I went too fast or too slow?
No, Ajit, the pace was fine.
Okay, all right.
This is Dipanjan.
Yeah. So which means I know Deepaka. Yeah. So the point is that I'm going to cover much less than I thought, but doesn't matter. So long as somebody understands something, we have done well, right?
Yes. I think the pace was fine, and also it was very clear.
Okay. All right. Bye.
Thanks, Ajit.
Thank you.
And so participants who could not ask their questions, I'll ask you to put them on the Google form.